Today I'll be presenting about work in progress theory called graded modal dependent type theory, or GrTT for short. And this is in collaboration with Harley and my supervisor, Dom. I'll start by giving a brief overview of some relevant history of grades and their uses. I'll then provide a bit of motivation for GrTT before introducing its syntax, the structure of typing judgments with a short example, and then revisiting some of the motivations. I'll then give a short overview of our implementation, which is called GrTT, which currently supports the basic constructions seen in the extended abstract, as well as tensors with basic support for grade inference. For quite a while, it's been known that linear typing is useful for representing certain forms of resource, allowing us to prevent discarding or copying data. For example, imagine you wanted to give a handle to a process and have the process give back the handle once it's finished, so you can do some cleanup. You want to make sure that the process hasn't given out any additional copies of the handle, and you want to make sure that the process doesn't end up discarding the handle before it can give it back. Linear types do have some downsides, however. There are many problems which cannot be represented linearly and require us to be able to discard or duplicate data. For example, imagine you needed to distribute copies of a record. This is an inherently nonlinear operation, as you're going to start with one copy and end up needing to produce many. To deal with this, linear logic provides a bang operator, which is used to denote data that may be used arbitrarily rather than just exactly once. And later, we see the introduction of bounded linear logic, which indexes bang with an element that allows specifying an upper bound on usage, allowing us to, for example, specify the maximum number of copies of the record we want to give out. More recently, we see this index generalized to be drawn from various semi-ring-like structures called coeffects, the elements of which we refer to as grades. This generalization allows capturing various properties, including exact usage, bounded reuse, and privacy levels. We then see the introduction of graded modalities. The main one of interest here is an S4 style graded necessity comonad, which allows internalizing grades to the syntax of terms, where, for example, the box RA here denotes the type of values that can be used with type A according to grade R. So you could use this to talk about numbers that can be used twice, for example. In GrTT, we take this notion of grading to the level of types. And why do we want to do this? There's a few reasons. Firstly, we do not generally have parametric reasoning in a dependently typed setting. Why? Because we cannot tell whether assumptions are used purely specificationally in the type, or if they have some computational use. What we will see later is that grading the type level will actually allow us to recover parametricity when we want it in a dependently typed setting. Another related problem is that dependent types can make it hard to reason about programs. When we pass an argument to a function, we don't know how it will be used in the function, and it's not always obvious whether the resulting type will be in some way influenced by the value of the argument. Grading the type level allows us to reason much more precisely about how assumptions can be used, and we will see later that in fact notions such as linearity and simple types can both be captured via grading. Further, such knowledge could be used to optimize program compilation and type checking. In GrTT, our implementation, we were able to achieve type checking speedups of 30% just from using grades to determine when assumptions could be erased from types. So how do we make a theory that can capture notions of grading at type level? Well, GrTT is parameterized by a pre-ordered semi-ring, which we draw grades from in order to track usage both computationally and specificationally. We often instantiate this semi-ring to be the natural numbers ordered by equality, which allows us to capture the exact number of occurrences of assumptions in terms and types. GrTT uses the same syntactic category for terms and types. We have variables, typing universes, lambda abstractions, applications in the usual syntax. On top of this, we then have dependent function types, which have graded binders. The grade S captures how the argument be used in the corresponding lambda abstraction or computationally, and the grade R captures how the argument be used in B or specificationally. We then also have doubly graded modalities, where the grade S captures computational use and the grade R captures specificational use. This is what our typing judgments So look like right of the O dot, we have a regular context gamma, which we often treat as a vector, a term T, the subject, and a type A, the subject's type. To the left of the O dot, we have a triplet of vectors, delta, sigma 1, and sigma 2, where we require that each of these vectors be of the same size as gamma. Suppose we have an assumption X of type B at index I in gamma, then we have the following. So the corresponding element in sigma 1 is a grade that captures the use of X in T, the subject. The element in sigma 2 is a grade that captures the use in A, the subject's type, and the element in delta is a vector of grades that captures the use of all assumptions prior to X in the formation of X's type B. Thus, we have sigma 1 and sigma 2 are vectors of grades that account for subject and subject type usage, respectively. And delta is a vector of grade vectors that describes how usage is accounted for within the context gamma itself. To get a better understanding of how the vectors relate to the context, subject and subject type, let us take a look at the typing of the body of the polymorphic identity. So there's a few things going on here, and we will break this down and look at the three vectors in turn. I'll speak in terms of exact usage, but this example is generally applicable to other semirings. So we see that sigma 1 has a 0 followed by a 1. And this describes that A is unused in the subject and X is used once, with the subject being the variable X. We see sigma 2 is a 1 followed by a 0, which captures the single use of A in the subject type, which is A, and the absence of X. We can then see that delta consists of an empty vector and a vector containing only the grade 1. Thus, we can see that the empty vector corresponds to A, and there are no assumptions prior to A. And the vector containing only just one grade corresponds to the single use of A in the formation of X's type. So I'm not going to go into detail for the rules, which can be found in the extended abstract, but to show that the previous example can be derived, I'll explain here how the variable rule works and show the derivation. So here we have delta captures the internal typing of gamma, and we carry this to the conclusion to preserve this typing information. Sigma captures how assumptions in gamma are used to form A, which is in the subject position in the premise. And then in the conclusion, we append sigma to delta to account for usage in forming the type of the assumption X, which is A. And we also use sigma in the subject type position to account for usage in the subject's type. We use a bold 0 to stand for a vector of an appropriate size containing only the grade 0. And we use this when capturing the usage of gamma in the constant universe in the premise. We use this same notation to explain that there's no assumptions prior to X that are used in the subject of the conclusion, which is the variable X. And finally, we explain that X is used once in the subject and unused in the subject's type with the final 1 and 0 grades. This is what the derivation then looks like. We can see that as we move up the derivation, we use sigma to capture the formation of the variable's type, which allows us to correctly manipulate the vectors. The type rule at the top simply lets us type universes under empty context. Recall earlier that I mentioned we could recover parametric reasoning with type level grades. How do we do this? Well, for certain semirings, including exact usage, we can use grades to determine exactly when assumptions can or can't be used. Moreover, we can distinguish assumptions used purely specificationally, which is something existing systems cannot capture. And then accordingly, we can capture parametricity by defining a universal quantifier as follows. Here we can see that the quantifier will ensure that an argument can only be used specificationally in the formation of B as the subject grade is 0. Using grades this way, we can use GrTT to capture different fragments of the theory, which can have different grade semantics. The example of parametricity above shows that for certain semirings, we can consider a stratified system F-like fragment, which admits a universal quantifier. Then, for example, we could also consider a simply type fragment, a linear fragment, and fragments that are pervasively linear in both terms and types. Okay, so now I'm going to give an overview of our implementation, GrTT. Okay, so in GrTT, we would define the polymorphic identity function like so. So we have graded binders. So here we need to say that we're taking an A, which is going to be a type, and we want to use this with grade 0 in the corresponding subject. So down here, we're going to have the subject, and what this is going to look like is this, where this lambda abstraction here will correspond to the subject for this grade. So we're using it for grade 0. But then in the rest of the type, we're going to use it twice. So we take an X, and similarly, this X is going to be used with grade 1, and the corresponding subject is down here now, and it's not going to be used in the remainder of the type. So this is the polymorphic identity, and it's well typed. But we have some shorthands we can start to employ to make this a little bit easier. So we can get rid of some of these arrows. And in fact, what we can start to do is sometimes we don't really want to specify all of the grades. So what we can do is replace them with implicits. So this underscore, what this means is the type checker is going to use an SMT solver to try and figure out what grade should be here. So if we run this, it's okay, but how do we know it's not just making us up? Well, what if we try and add something to this? So if we know this grade has to be 2, and so we're in an exact usage semi-ring here, we know there's nothing we can add in an exact usage semi-ring to 3 to get 2, so this shouldn't work. And yeah, we get a grade error. Our error messages aren't great at the moment. They're a bit better for type errors. So if we get rid of that and we replace this with an X, then we get a slightly more informative error, but our error system does need some work. What we can actually do then is, if all of our grades are implicit, we can just get rid of the grades on the binders, and we end up with a fairly concise version of the identity. But the grades are still happening, they're just happening in the background. We're just telling the type checker to try and figure it out for us. What we can then do is, we know that the 0 grade can, for any semi-ring, denote something that is unused. So we can define a constant function. And what we're saying here is, well, we're taking this A and this B, which are types, and notice that we actually say, well, this A is going to be used twice in the formation type, and this B is going to be used once, because we're going to take an argument of type A, and that's the one we want to give back. And when we take the argument of type B, we're going to discard it, so we wouldn't expect this B type to be used more than once. And yet we say we've got this X of type A, and we're going to use it once down in the subject, which is here. And then we take this Y and we grade it with 0 in both the subject and the subject type so that we can get rid of it. And again, this is exact usage. If you have an argument which is formed with some resources which can be used some amount of times, say like 3 times, and your function is going to use that argument twice, then all of those resources are going to get scaled. So if you've got those 3 uses and you're going to use all of those 3 uses twice, you're going to end up with 6 uses. And this is shown here by saying that, well, we've got this duplicate function, and it takes some argument X, which represents some resources which can be used twice, and it splits those into this pair. So we need to say it's used twice because we're actually going to be duplicating this in a result. And then for dupe, what we're doing is the same thing, but notice now we need to say that it's used with grade 4 down here, because whilst we're taking this thing in once, we're actually going to be using it 4 times. And then dupe, which is just duping that whole thing again, we now need to use it 8 times because it scales each time. So it scales from 2 to 4 and then 4 to 8. As mentioned before, we can start to encode parametricity in a controlled way in a dependently typed setting. And what we can do here is say, well, it's worth noting that we don't currently have first-class grades, so we have to specify these explicitly. So we could define a for all 1, and we can do a for all 2. And what each of these are saying is, well, we have some input type, which is what we're which is going to correspond to this A here. And then our B is going to correspond to this B. And what we're saying is, well, given some B, which is a function which can take an X, and in this case, an X which is unused in the subject, because this grade 0 in an exact usage semi-ring means that it cannot be used, but it's used with grade 1 in the subject's type. So we know that B is going to take this argument, it's going to use it once to form the type, and it's not going to use it at all in the subject level. And this allows us to capture this notion of parametricity, where we know these arguments aren't being examined at the level of the subject, but they can be used in the subject type. So this one is saying it's going to be used with grade 1 there, and this one is going to be used with grade 2. Then what we can also do is something similar for linear functions. So here we're saying that we're going to take an argument which is used with grade 1 in the subject and grade 0 in the subject's type, so linearly. And then we can start to use this along with the rules to build up programs where we don't really need to specify grades because they're encoded in these functions already. So this identity is saying that, well, for any type which can be used twice in type formation but is not used at all in subject formation, we can produce a linear function which takes some value and then produces a value of the same type. Sometimes we want to consider data that can be used in different ways for each of its components. So we don't always want to consider how data is used as a whole. Sometimes we want to break it up and use the components in different ways. And graded modalities allow us to do this. So with a projection function, what we can do is say, well, given a pair where it's a pair, it's got an A in it and it's got a B in it, but we use this type former, which is the graded modal type former, to say that, well, this B, it's used with grade 0 in the subject and grade 0 in the subject type, which means we can just get rid of it. And then we can use this in this elimination form down here to actually discard that completely and just do a first projection. And then likewise, we can do a second projection by grading on the first element rather than the second. And in this way, we can do various interesting things with data. So if we've got like composite records, sometimes we just want to examine parts of those records or treat them in different ways, and graded modalities allow us to do this. And then the last thing I'm going to mention is that we do have support for some other semi-rings. So this is an example of a privacy level semi-ring where we have these 3 grades, irrelevant, private, and public, which are ordered. And this is just an example of a function where we're taking the least upper bound to take a function which is irrelevant, least upper bound private, to a function which takes its argument at private. One of our goals is to add support for user-defined semi-rings at some point, along with the first-class grades, but we currently don't have support for that, so that's very much future work. And this indeed runs. So to summarize, GrTT captures both computational and specificational usage, which allows us to recover parametricity when we want it in a dependently typed setting. And it allows us to consider different fragments of programs with different grade semantics. We have a work in progress implementation called GrTT, which is a proof of concept that these ideas can be used in a practical setting. And this work fits in with an umbrella project known as the Granular project. Future work for this project includes improving the implementation and using it to explore more semi-rings, as well as developing theory for first-class grades and adding this to the implementation. And the last thing I'll mention is type synthesis, where we will explore using grades to help in the synthesis of both terms and their types. Thank you.